Alright guys, here we go with the next section. It's on ellipses, and we go like this. An ellipse is a set of points where the sum of the distances from two distinct points called foci, that's the plural of focus, foci, the sum of the distances from two distinct points is some kind of a constant, okay? So let's put a point up here, xy, and let's call this focus number 1, and this will be focus number 2. Together they are called foci, plural. Well, if I draw a line segment from that point to that focus, and another line segment from that to that point to that focus, I'll call that distance 1, and this one is distance 2. What I'm saying is that no matter where you move this point, the sum of the two distances will be constant. So that d1 plus d2 is equal to what I'm going to refer to as the magic constant for the ellipse. Now, we won't use that term all that often, but I'm going to use it now for a minute or two. The definition, the line, there's a whole bunch of information about ellipses that get you caught up. The line that passes through the foci intersects the ellipse at two vertices. Okay, so if I had a line that went through these two foci, at the end of the ellipse where they connect, those are going to be called a vertex. Each one of them will be a vertex, and the plural is vertices. Now the chord, that's a line segment that fits inside something like a circle, that connects those vertices. That's called the major axis. Now I'm going to draw a picture of that on the bottom so it'll make sense to you. Ready? There's the two foci. We'll call this one focus 1. This will be focus 2. Now if I make a line segment that connects these two vertices, I'll call this a vertex. And at the bottom we'll call this a vertex. If I connect them with the line segment, it'll go right through these two foci. That line segment is what we refer to as the major axis. Alright, so there you go. The ellipse is made up of all points where the connection from that point to both of these foci, the distance is constant, the magic constant. And if I connect these two vertices, I get a line segment called a major axis. Definition, the midpoint of that major axis is called the center of the ellipse. So we can find this right about here, similar to the center of a circle, wouldn't you say? That is going to be called C, and I'll put a little arrow up there. That is the center of the ellipse. Okay, I got another one. A chord that is perpendicular, makes a right angle, to the major axis that goes through the center is called the minor axis. So I believe I have one more thing to draw on here. I need to make something that goes right angle to the major axis and goes through the center. This thing here will be called the minor axis. Okay, now different authors do something else at the end of the minor axis here. Your author doesn't, for this one, this edition that we're teaching out of this year, doesn't have any name for these kind of things, but I'm going to put points here because other places do have names for this, and we will call this a co-vertex. At the end of each one of the, or at the end of the minor axis on each side is something called a co-vertex. So there, look at all the stuff we got here. We got two axes, a major axis and a minor axis. We have a center. At the end of the major axis is two vertices. Along the major axis is the two foci that define the thing in the first place. Along the minor axis, at the end of it, there are two co-vertices. That's a lot of stuff. Let's go to page 2. Okay, we got to break down some real important distances here for you to be able to do problems with ellipses coming up. This is, oops, I lost a light there. This is something that comes up more often that, oh man, my light really broke. I pointed it at my face and it came back on. Now I'm blind. I love this school year. Okay, anyway. Where was I? ACT, SAT. These are the, if this is going to show up, this is it right here. I've seen it, the ellipse more than anything. Okay, the important distances. Well, let's put a center right in the middle here, and we'll call this focus 1, and this will be focus 2, and we'll put a C for center, okay? The first distance I want to go over is from C out to this vertex here. A will be the distance that we will call half of the major axis. Can't believe I just blinded myself with a lamp that went out. There was no reason for that to go out. It just went out, and then it came back on, and now I'm blind. So this is the distance A right here, from here to there. That's the distance A. B is 1/2 of the minor axis. So it'll be smaller every time, right? That should make sense to you. So if I draw a minor axis up here, right there, B is this length right here. There you go. There's A and B. Now I put a C in there for the center, and that may confuse things because C as a distance, not as that point, C for the center. C is the distance from the center to a focus. That distance will be the same no matter which direction we go. So I'll draw it over here. That distance is C right there, from the center out to that focus. Okay, or another way to think of this is, let me draw in my axes on this ellipse also. So there's an axis, they meet at the center, of course. Okay, so if my point XY happens to be here, okay, just like my point on the other page where the sum of the two distances to the two foci is the magic constant. Look, here's one, that's D1, and then here's the other one. I'll draw it just above. There's D2. Okay, well, look, isn't this distance D1 the same as this one over here? From that vertex to that focus has to be the same as from this vertex to this focus. That's really D1. Okay, so let's think about it. I mean, this distance right here is C, and this distance right here is A. From the vertex all the way to the center is A, and from that focus to the center is C. We need to notice a couple of things here. Think of a vertex. That's where I have my point, right there. The sum of the distances to F1 and F2 is equal to our magic constant. The distance to F1 for that focus, if this is going to be F1 right here, it would be A, this distance, minus C, this distance. If I wanted to know that right there, D1, it would be all of A minus all of C. A minus C. And then the distance to F2, well, look at this would go all of A, and then you got to add C. So that would be A plus C. So the sum of the distances, which is the magic constant, right? The distance from one focus and the distance to the other focus, those two added together, that's going to be A plus C plus A minus C. You guys, the C's cancel and it's 2A. The magic constant is 2A. Now imagine a point at the end of the minor axis. This point would actually be equidistant from both foci. It would have to be. Okay, let's draw it. So I'm going to draw a major axis, and I'll put a point in the middle as a center, and I'll draw a minor axis. Okay, here's my point XY. That's at a co-vertex. Isn't it got to be the case that this distance is the same as that distance? Right? D1 has to equal D2 here. Both distances are equal because that point is right in the middle of them. Their sum, of course, is 2A because I just learned that the magic constant is 2A. So they both equal A. D2 in this particular example is A, and D1 is equal to A when that point is at the end of the minor axis. So the vertex, it creates a right triangle here, doesn't it? It creates a right triangle right there. So look, this is C from this vertex to this focus, that's C. From this, from the center to the focus, I said it wrong. From the center to this co-vertex is B, and we just learned that this is A. That's the same A that goes from here all the way out to here. So it's got to be the case that B squared plus C squared is equal to A squared, which is going to look real weird to you guys, but that's going to be true for every ellipse. b squared, b being the distance from the center to a covertex, c squared, c being the distance from a center to a focus, and a squared, a being the distance from the center out to the vertex. All right, let's go to the next page. We got some more information stuff before we get into doing any problems, and I want to get all the way there today. Okay, so I'm going to put another point, and we're going to prove something to you. I'm going to start to prove something to you. I'll show you where the equation for the ellipse comes from. I'm going to call this focus 1, and this is focus 2, and I'm going to draw these two distances. We'll call that D1, and we'll call that D2. Okay, now I want you to put point right in the middle and call that HK. Okay, if that's the case, and the distance from this center to this focus is C, isn't this point H plus C comma K? Take a look at that and make sure it makes sense to you. If the center is HK, to get over to that focus, I got to go C units to the right. Wouldn't you just add C to the X variable? And then K, it doesn't go up and down from there, so it's just K. So that means that this focus, this point right here, would be H minus C comma K. All right? Imagine a point anywhere on the ellipse. Knowing that the sum of the distances to the foci from the point is equal to 2a, and using the center of the ellipse as HK, that would make the coordinates of the two foci the two numbers that we just said, H plus C comma K and H minus C comma K. So the two distances, that distance and that distance, we use the distance formula for the parabola and for the circle. Here we go one more time. D1 would be the square root of x minus x2 minus x1 squared. So I'm going to go x minus, in parentheses, h plus c, that's all squared, plus y minus k squared. Those two x's subtracted squared, and those two y's subtracted squared. And D2 would be that x minus this h minus c, so x minus, in parentheses, h minus c squared, and then that y minus that k squared again, y minus k squared. Those are my two distances, and the definition of an ellipse is that I add up the two distances, they are equal to the magic constant. So this is the beginning of the proof for the equation, the standard form of the equation for any ellipse. You ready? It will go like this: the square root of x minus h minus c squared. I just took that and distributed that minus right there. You see that? Plus y minus k squared. Plus, because I'm supposed to add the two distances together, the square root of x minus h plus c squared. I just distributed that minus to both of these. Plus y minus k squared. And when I add the two of them up, what are they supposed to equal? They're supposed to equal 2a. You guys, that's where it starts. And what do I do in order to make this look like something we can work with? Which h's and k's and things being squared, you would square both sides to get rid of the square root signs. And you would substitute using b squared plus c squared equals a squared, which we found in that triangle on the last page. And so look, you get dot, dot, dot. I'm going to say more proof stuff if you guys want to see it. You know what? I'll tell you what. I don't know how many of you guys watched the last time I did that. If you want me to, I'll write out a proof for this, and you guys can watch that video too. My guess is nobody wants to see it, but if you guys do, let me know and I'll do it. The standard form of the equation of ellipse goes like this. If the major axis is horizontal, which would look like this, there's your major axis, and it is horizontal, parallel to the x-axis. But after we do all of this work, we would end up with this: x minus h squared over a squared plus y minus k squared over b squared, and it would equal 1. That is the equation of an ellipse, standard form of the equation of ellipse, when the major axis is horizontal. So here's when it's vertical. Ready? Y minus k squared over, what is that? Sorry. Squared over a squared plus x minus h squared over b squared is equal to 1. You could rewrite the order of these because it's plus. The big idea is a is bigger than b. You got to keep that in mind from an ellipse. So whatever the bigger denominator is under, see this one's under x, that's x squared. If the x squared is over the bigger number, that means the major axis is horizontal. If the y squared is over the longer of the two, it means the major axis is vertical. All right, woo, that's a lot of stuff. I went through that pretty quick. Let's go to the next page and see what we can do with this hot mess, okay? I'm summing up some distances for you, and then look, we're going to get to work with a couple of equations. This is going to take us 2 days, I think. We'll do this, and then we'll do some extra practice, and I've got a little more to say, I think, after these notes. Okay, so let's draw in the major axis here. Let's put the center there, and let's draw in the minor axis. Okay, I think we know that the distance from the center to the vertex is A. I think you guys got that. And I'm going to do this from the distance from the center up to the co-vertex is B, and then this distance right here is C. Okay, the length of the major axis is clearly A plus another A. It's 2A. That is also the magic constant for the ellipse. The length of the minor axis is 2B. The distance from the center to a focus is C. The distance from a center to a vertex is A. And the distance from the center to the co-vertex is B. Hopefully, you guys just looked at this and went, yeah, all that makes perfect sense. And what's the relationship with all those distances? One more time, B squared plus C squared is equal to A squared for all the reasons that I just pointed out on the last page. Okay, here we go. Find the standard form of the equation of an ellipse with a focus, or foci, at 0, 1, 4, 1, and a major axis of length 6. When you're given this information, it doesn't have to be a great graph, just sketch it so you get a feel for what's going on. So I'm going to draw a little bitty XY coordinate plane there. I'm going to go to 0, 1, so I go up 1 and put a point, and I go to 4, 1. 1, 2, 3, 4, and then put a point. The center is always in between the two foci, so I can put a point right in the middle there, and I can see without even having to do any math, it's at 2, 1. Okay, so the center is at the point 2, 1, and if the foci are going this way, the axis is definitely horizontal. So if we've got a horizontal major axis, then the x squared will be over the longer of the two numbers. Okay, this is going to go like this. X minus h squared over a squared plus y minus k squared over b squared, and that's going to end up having to equal 1. Now they say that the major axis has a length of 6, so that means if 2a equals 6, that a equals 3. Okay, so from the center, which is at 2, 1, that gives me this information. X minus 2 squared, and then I have y minus 1 squared. As soon as I find a and b and square them, I'm done. I got my equation. Well, a is 3, so this is clearly going to be 3 squared. It's 9. All I got to do is find b. Well, this distance was a center to a focus, and it was 2. So we know a is 3, and we know c is 2. I'm looking for b squared. I have a way to find b when I have 2 of these. So I go b squared plus c squared is equal to a squared. So b squared plus 4 is equal to 9. I just squared them and put them in there. I hope you're okay with that. That means that b squared is equal to 5. Now the math person in me wants to take the square root and call this plus or minus 5, but I don't have to because I was just told to write the form of the equation on the line, and there it is. X minus 2 squared, where did I get my 2? I found my center in between these two foci. It had to be 2, 1. So that 2 turns into x minus 2 squared. This is clearly 1 up since both of these are 1 up and the center is in the middle of the foci. So that 1 goes right here. I have y minus 1 squared. They tell me the length of the major axis all the way across is 6. That means a has to be 3. And so 3 squared is 9. And then I used this weirdo version of the Pythagorean theorem to find out that b squared is equal to 5. All right, sketch an ellipse. Name the center and the vertices. Well, we're going to name the co-vertices as well. We're going to add to that. So I'm just going to write it in there. Co-vertices also. Okay, it looks like I might have to complete the square. Actually, I don't have to complete the square. I'm just going to write out 4x squared plus y squared is equal to 36. How do you know you don't have to complete the square? There's no x term to put in the middle, and there's no y term to put in the middle. I don't need to write out the parentheses and do anything. But if you look at the equation here, and if I go back one, if you look at the equation here, they're equal to 1. Well, in this general form, it's not equal to 1. It's equal to 36. So how can I get a 1 there? I can divide by 36. Just divide everything by 36, and that's how we end up with these numbers in the denominator. On the right, we now have 1. There's nothing to cancel here, so I have y squared is equal to 36. And over here, these do cancel, and I get x squared over 9. Okay? Because the bigger one is underneath y squared, that means we have a vertical major axis. Okay, that's important. So A is equal to 6. And if you look over here, B is equal to 3. Now I don't know what C equals yet, and I'm going to need it because that's the distance from my center to my focus. Oh, it didn't say to find any focus, so I don't even have to deal with C. That's nice. Let's find, this has got to be a center at 0, 0, because that's like having x minus 0 squared, right? That's what that's like. Okay, to go up and down to get to a vertex, I got to go up and down 6 units. So 1, 2, 3, 4, 5, 6. And that is the point 0, 6. So I'm supposed to write what the center is. Okay, the center is 0, 0. I'm supposed to write what the vertices are. Well, one of them is 0, 6, and I'm also supposed to go down 6. 1, 2, 3, 4, 5, 6. So that's going to be the point 0, negative 6. And then to get the co-vertices, which this didn't even ask for, I go 3 right and left. 1, 2, 3. And the co-vertices, I'm going to have one at 3, 0. And when I go backwards, 1, 2, 3, I'm going to have one at negative 3, 0. All right, sketch the ellipse. This was somewhat easy because I didn't have to complete the square. That happens when the center is at 0, 0. If it asked me to find these foci, I would have to go find C, and then I would have to add C to this 0, and I'd have to subtract C from that 0. But it didn't ask me to, so I'm not gonna. Next page. Oh, here's our last one for today. Man, I know I went fast, and that's a lot of stuff, so trust me, tomorrow we're going to let this sink in, and we're going to do a couple examples. Sketch the graph of an ellipse with that graph. Now look here, there is an x term, and there is a y term, so now we're going to get into completing the square. We're going to find the center, the vertices, and the foci. Let's find the co-vertices as well. We got plenty of paper, and this is our last problem for the day. So I'm going to complete the square first. Here we go. I got x squared plus 6x. I'm going to keep those two in parentheses by themselves. Then I'm going to go 4y squared minus 8y. I'll keep those in parentheses by themselves, and we'll move the 9 to the other side of the equation, so it's minus 9. Here I can complete the square. Half of this is 3, and 3 squared is 9. Here I cannot take half of this negative 8. You guys got to remember this. I cannot complete the square if there's a number in front of the squared term. You have to factor it out first. So I have x squared plus 6x. I'm just going to leave that the way it is because I got work to do on my second set of parentheses. Use the distributive, that's supposed to be distributive property, to take the 4 out, and I get y squared minus 2y. A real teacher would edit that out. I'm not going to do it. Okay, so there we go. I took a 4 out from here. I took a 4 out. Make sure you take the 4 out from both of them. You can screw this up real easy if you try and complete the square too quickly. Okay, half of this 6 is 3, and when I take 3 squared, I get plus 9. I put a plus 9 there. I have to put a plus 9 there. I take half of this, it's negative 1. And when I square negative 1, it becomes plus 1. But I don't put a plus 1 there because it's times 4. Don't forget that it's times this number. So I really have to put a plus 4 over there to go with that. This becomes x plus 3 squared. I've got a 4 right here, and it becomes y minus 1 squared. Negative 9 plus 9 is 0, and I added a 4. So there we go. There's me completing the square twice. Real tricky things, guys. You got to take that number out. It's got to come out from here, too. Also, when I take half of this and square it and add it, we got to remember to multiply it by our coefficient, before we add it to the other side. Now what's my last step? I'm going to divide by 4. I'm going to divide by 4 everywhere, excuse me, to turn that into a 1. X plus 3 squared over 4 plus these 4's cancel, and this is y minus 1 squared over 1, and of course those cancel and give me 1, which is what I wanted in the first place. Okay, check it out. Where's the major axis? The bigger number is under the x squared, so the major axis is definitely horizontal. I know enough now, right now, to say that the center is equal to negative 3, 1. I know that a is 2 and b is 1. That's a squared, right? If a squared is 4, then and b squared is equal to 1, then a is 2 and b is 1. I do have to find the foci, so I'm going to need c as well, so I might as well just get that out of the way right now. B squared plus c squared is equal to a squared is the Pythagorean idea for an ellipse. So 1 plus c squared is equal to 4. That's a squared and b squared, right? That's what just happened right there. So c squared ends up being equal to 3, and c is the square root of 3. Okay. So my center's at negative 3, 1. 1, 2, 3, 1. That's my center. Let's just work on, if a is 2, let's find the vertices first. Okay, once the center, the vertices seem to be the thing that we'd want to do next anyway. So the bigger number's under x squared, so I'm going left and right here, and I got to go 2 units. So I go 2 units that way, and I have negative 1, 1. I go 2 units backwards, and just subtract 2 from that, I get negative 5, 1. Right? There's my vertices. Let's find the co-vertices, because they're just as easy as finding the vertices. So I go back to the center of negative 3, 1. I go up and down for a co-vertex, and I only go 1. So if I go up 1, that's the point 3, 2, isn't it? Negative 3, 2. And if I go down 1, I'm right on the x-axis there. That'll be the point negative 3, 0. So you can see my ellipse. That's a little baby ellipse. There's not a whole lot going on there. You don't have to waste a whole lot graphing that. Let's see, I found the center, I found the vertices, I found the co-vertices. Now I got to find the foci, which are square root of 3 units away from the center. Now pay attention to this, I'll go a little slower with this. I got to go to the point negative 3, 1, and I got to go to the right the square root of 3 and to the left the square root of 3. In an ellipse, it'll never be further than the vertex. B is always shorter than A, right? So square root of 3 to the right, look how you write this. The foci. I'm going to say the negative square root of 3 plus the square root of 3. Write it just like you say it. And then the y value is 1 because I'm going to the right. It doesn't go up or down. And then the other one will be this negative 3, and it'll be minus the square root of 3, comma 1. That's a pretty big problem right there. Look at that. You had to complete the square twice. You had to find the center. Figure out where the major axis goes. In this case, since the bigger number is under x squared, it's horizontal. Find the vertices. Find the co-vertices. Solve for c with the Pythagorean theorem. And find your foci. That is a lot in one day. I'm sure you guys may have to pause and go back and look at that. But I'm going to put a couple of problems on my math lab. I'll try not to put anything too stressful. And then let's see how everything goes. And we'll follow up with ellipses tomorrow. Have a good day, everybody.